Unit 3.4 Linear Programming. So in this class we're going to learn how to solve problems using linear programming. So two terminologies that you have to remember in this whole chapter. First, feasible region. The second one is objective function. Feasible region is referring to the intersection area that we learned from the last chapter in the linear inequality system. So a quick recap: when we have two linear inequality and say if the intersection area right here, okay, I use different color to highlight it for you. So this is the intersection area in the inequality system, and in linear programming we refer this as the feasible region. Every single point in this region will make every equation in the system become true. The objective function helps us determine the maximum or the minimum value of this solution set. The next concept that we have to learn is the vertex principle. So according to the vertex principle, say if our feasible region is the shading area right here, the maximum or the minimum value of this solution set will only lies on the vertex of this feasible region. Here are the general steps to help you solve linear programming problem. First, based on the constraint, is actually the linear inequality system, but in linear programming we call it constraints. So based on the constraint, we determine the feasible region. So in other words, if you're given a system of linear inequality, say y bigger than 0, x bigger than 0, and x plus 2y bigger than 12, or 3x minus 4y less than 15. So these are the constraints. So based on this constraint, you can construct or determine the feasible region. Once you have the feasible region, you have to identify all the vertices. In other words, you have to find the intersection points of the linear equation. Let me draw you an example right here. So if you have feasible regions like this, I just give you a simple example. So if this is the feasible region, this is x-axis, y-axis. So the vertices are all this. So 0, 0 is easy. But for the other 3 points, for the other 3 vertices, they're basically the intersection of, I use different color to highlight for you. So this vertex is actually the intersection of the y-axis and this linear equation. And let me use another one. Another color. So this time I use a blue. So this vertex is the intersection between these, and this time is this one. And the last vertex is the intersection, I use black this time. This vertex is actually the intersection of this one, this linear equation, and the x-axis. So to find all the vertices, you are basically trying to find the intersection points of different linear functions. Now, let me give you an example of how to set up an inequality system to maximize or minimize value of a solution sets. This is what linear programming is all about. You're given a set of constraints, which basically a system of linear equalities. So based on the set of constraints, we can graph the inequalities. Let me walk you through the whole process. So the first step, of course, we're gonna set this whole inequality x plus 2y less than or equal to 5 to x plus 2y equal to 5 to draw the boundary. This is the first step. So then we use the table values to draw the boundaries right here. So the line here, the red line here, represent x plus 2y equal to 5. The next step, of course, we have to find which part, the plane A or plane B, that we're going to shade. So we use the critical point 0, 0 to test it. So 0 plus 2 times 0, is it really less than 5? Of course, 0 is less than 5. So we're going to shade this part. So this whole part represent x plus 2y less than 5. So we just know this part represent, this shading part represent x plus 2y less than or equal to 5. And now let's do the second inequality. So same thing, we're going to set x minus y less than or equal to 2 to x minus y equal to 2 to draw the boundary. So same thing, we're going to do the table values to find 2 points, the x-intercept, y-intercept. Then we end up getting these blue lines. Okay, I'm going to change the color to blue to highlight it for you. So this line represent x minus y equal to 2. Now we use the testing point 0, 0 to test if 0 minus 0 will less than 2. The answer is yes. So we're going to shade this part. X bigger than or equal to 0 or y bigger than or equal to 0 is basically referred to, let me take this area. So the only region which cover every single thing, I mean the green square and the blue line and the pink line, are only this area. So I'm just going to color it for you so you can see it. How about this time I pick black. So this whole area are the feasible region, and in other words, any points here will make all these inequalities become true. So this is the feasible region. So based on the feasible region we find from the last PowerPoint slide, the next things we have to identify all the vertex. So the vertex Q, R, S, T are listed here. So they are right here, and right here. Remember, this is only an example to show it to you. So they give you all these coordinates already for x and y value of each vertex. So sometimes you have to find it yourself. The way you find it is just to solve the system of equation of these two lines to find the intersection point. Alright, in this case they give you all these coordinates already. So the next step you're going to do is to evaluate each single vertex, because according to the vertex principle we know the maximum and the minimum gonna be lying on one of these points. So when we plug in the x and y coordinate of the vertex, for example in here, this is the objective function p equal to 2 x plus y. This is the objective function, and based on the objective function we just evaluate each vertex by plugging the x and y value inside of it. So for the first vertex we come up with this value of 0. For R, we got 2.5. For S, we got 7, and the last vertex we got 4. So if I compare all these values, you know this is the minimum value, and of course S is the what? Maximum value. The biggest challenge in linear programming is the real-world application, because in this case you have to set up your own constraints and find your own objective function and follow the process that I just showed it to you in the last couple PowerPoint slides. So here's a real-world example for you. In this example, you're asked to produce some t-shirts and sweatshirts to sell to make some money. So of course your goal, your target is to maximize your profit. But you cannot just produce as many t-shirts as you want or sell as many as sweatshirts as you want, because there are constraints. For example, here's some constraints. You can only have 20 hours, the most, to make shirts. And you cannot spend more than $600 on supplies. And you have to sell at least 50 items. So these are constraints. At the same time, you make profit out of a t-shirt for $6, and you make a profit of $20 if you sell the 3-color sweatshirt. And here's some constraints as well. You take 10 minutes to make the t-shirt, and it takes longer time to make the sweatshirts. And the cost of supplies for this t-shirt is $4, and the cost for this sweatshirt is $20. So there are a lot of numbers lying around. So you have to put everything together by first go back to the first step of solving linear program problems. First, you have to try to set up all the constraints. In other words, you have to list all the linear equalities, and then based on that, you're gonna graph it and find the second thing, find the feasible region, and then identify all the vertexes, and then fourth, you have also come up with your own objective function. Your objective function this time is to maximize the profit. So you have to find your objective function. Then based on the objective function, evaluate each vertex and try to find the maximum value. That's the maximum profit. So in order to solve this problem, we have to organize the information so we know what to do. So first, as all the problems in algebra, we have to do let x. So we're gonna let x be the number of t-shirts that you're going to produce to maximize the profit. And of course, y is going to be the number of sweatshirts that you're going to produce to maximize profit. So based on the information that we just got from the last PowerPoint slide, we know in terms of minutes, remember we have 20 hours only to do that. So 20 hours, if you times 60 minutes, you got 1200 minutes. And if you still remember, the t-shirt needs 10 minutes to produce, and the sweatshirt needs 30 minutes to produce. In other words, if you produce one t-shirt, it takes 10 minutes. If you produce two t-shirts, you need 20 minutes. If you need 3 t-shirts to be produced, you need 30 minutes. If you produce X, then you use 10 times X. So you need 10 times X minutes to produce t-shirts. Same reason applied to sweatshirts. So we got 30y. And you have to sell at least 50 items. So X plus Y got to be bigger than 30. This is most. This is at least you have to sell 50 shirts together. The cost and you need or the supplies that you need to produce t-shirt is $4. So if you produce X t-shirt, you need $4X of supplies, and then you need 20Y for the supplies, for the cost for producing sweatshirts. So add together, you cannot have more than $600 for your supplies. And X got to be bigger than 0. You cannot produce negative t-shirt, you cannot produce negative sweatshirt either. So these are the constraints. The whole thing is the constraints. And the objective function this time is to maximize the profit. So when you sell $1, when you sell one t-shirt, you make $6. When you sell one sweatshirt, you make $20. So if you sell X t-shirt, you're gonna make $6. And if you sell a Y t-shirt, Y sweatshirt, you're gonna have $20. So this is the objective function. Once you set up the constraints, you graph them and determine the feasible region, and then find each vertex. Again, you might have hard time to find all this because right now they show it all to you, but in the test or in other questions you have to learn how to solve the system of equation of these two lines and then find the intersection point, which are the vertex. So you have to learn these skills, which we learned that before in the last chapter. So once we find all the vertex, the coordinates of each vertex, we can evaluate based on our profit function, which is 6x plus 20y. So then, after we evaluate each single vertex, we can see the maximum is $750, which lies on the vertex C right here.